Thank you. Now we'd like to move on to Michelle.
All right, thank you very much. Let me share my screen. Okay. Minimize here. All right. So hello, everyone. My name is Michelle Worthington. I'm a PhD student in Ty Cannon's lab at Yale University. And I'm really excited to talk to you all today about some work that we've been doing, specifically on using a joint modeling approach for individualized prediction of conversion in youth at clinical high risk for psychosis. And there was a bit of a nod to this earlier, so hopefully this will be interesting. So just to start with a little bit of background on existing efforts to predict conversion in this population, I'll focus specifically on some existing clinical risk calculators. So these risk calculators are multivariable models that estimate an individual's likelihood of converting to psychosis. And several have been developed and validated, including several by many of those whose primary investigators are attending today. I've included here just a screenshot of the online version of the Naples 2 risk calculator, where you can see that the baseline assessments for clinical assessments for symptoms, demographics, and neurocognitive functioning, when you put into the model outputs the individual likelihood of converting to psychosis after 1 year and then 2 years. So all of the risk calculators listed here rely on baseline data, which is primarily clinical data, although there's been some work with neuroimaging data as well, and overall are able to achieve a prognostic accuracy between about 65 and 80%. So overall, these models do perform pretty well, but there's definitely room for improvement in this predictive accuracy. So the question that's really driving the work that I'm presenting today is, can we improve the prediction of psychosis onset at the individual level by incorporating short-term longitudinal change in clinical, neurocognitive, and functional measures? So to answer this question, we employed a statistical approach called joint modeling. And this approach combines both longitudinal linear mixed effects models with time to event regression models to estimate an individual's likelihood of converting. What's unique about this approach is that the risk estimates are updated beyond the baseline visit, which is different from existing risk calculators, so employing dynamic prediction. So said in another way, this method assumes that the risk estimate will depend on the values at a given time point. So this is a graphic that just kind of nicely illustrates how joint modeling would be useful. As you can see that as we acquire more data here on this sort of imaginary measure for this patient, the likelihood of survival or conversion changes, as indicated by the survival curve here, which could be informative for us as to how to effectively intervene at these early visits. Joint modeling has been implemented in the clinical high-risk population in a few instances, and overall, prior studies with joint modeling have shown that these models outperform baseline models, and ultimately that we can really gain a lot of information by incorporating short-term change of clinical measures into our prediction frameworks. So now I'll spend some time just laying out the specific methods that we used in our study. So in terms of our sample, the participants were from the third wave of the North American Prodrome Longitudinal Study, or Naples 3, who completed both baseline and 2-month visits. So this left us with a sample of 574 participants, 49 of whom eventually converted. And to select variables that we included in our analysis, we started with a pool of about 50 different clinical, neurocognitive, and functional items that came from a bunch of different measures. And then we performed a linear mixed effects models with a time by group interaction term predicting each of these variables, and then selected variables that had a significant interaction term. We then built our predictive models in the joint modeling framework, which includes a baseline time to event model, in addition to a longitudinal model. And then we tested the performance of these models in correctly predicting eventual converters through a repeated internal cross-validation framework using 70-30 splits to make sure that we had an adequate number of converters to predict in each of the testing samples. So the results of the feature selection process produced 7 different predictors that had a significant time by group interaction term. And these included the total SOPS score, One of the disorganization measures odd behavior and appearance, decline in social functioning, decreased expression of emotion, one of the negative symptoms, grandiosity, a positive symptom, perceptual abnormalities, another positive symptom, and then an item from the sleep questionnaire, which was getting in and out of bed around the same time every day. So once we had these variables, to estimate the predicted risk of conversion, we built 7 individual joint models and selected the one that performed best, but also demonstrated differential worsening in converters. And so I'll unpack a little bit more of what the joint modeling consists of here. So for the baseline model, we're using the original Naples 2 risk calculator model, which consists of these variables that include demographic, symptom, and neurocognitive variables in addition to overall functioning. And then this was the structure of the longitudinal models that we used, which was essentially the same structure that we used in the feature selection process. So then we combine these models into a joint model. And I just want to make it clear that in this case, we're examining 7 different joint models to examine the unique effect of adding each of these longitudinal measures to the existing baseline model to examine the additive power of each, the predictive power of each of those measures. So now I'll just walk through some of the performance results that we got with our joint models, and the metrics that we're using to evaluate performance include area under the curve as indicated by these yellow bars that will show up, sensitivity, specificity, and balanced accuracy as measured by this navy bar. And they're all measures of discrimination between correctly predicted converters and non-converters. So first, I just want to point out that we see that the baseline risk calculator model performs at approximately the same level that we would expect based on prior work, which is with an AUC of about 0.72 and a balanced accuracy of 0.65. So then for the 7 joint models that we built, we really see a range in performance where several of the models demonstrate significantly higher performance as compared to the baseline model. And some of the models perform about comparably to the baseline model alone. And for the well-performing models, we're seeing AUCs in about the upper 90s and balanced accuracies in the 90s as well. So this is really a significant improvement in terms of predictive performance. And as you can see, we have the luxury of having multiple models that perform really at a high level. So we do ultimately want to select one of those that makes sense in terms of interpretation. So this leads me to discuss a little bit more about the final model that we selected, which was the negative symptom item, decreased emotional expression. So in the feature selection process, we see that this item shows a pretty clear differential where converters actually worsen as compared to non-converters. So converters in the blue, non-converters in the red. This was not necessarily the case for some of the other variables that we found during the feature selection process. And this was important that we detected this pattern so that we're specifically understanding conversion where symptoms probably worsen as compared to another clinical phenomenon like remission or maintaining CHR symptoms. And again, so we see that this model does perform significantly better than the baseline model in this side-by-side comparison. And you can see on the right here, the specific metrics where the AUC increases from 0.72 to 0.99, and the balanced accuracy increases from 0.65 to 0.94. Okay, so to conclude, in this talk, I presented some exciting findings about how joint modeling might be able to help catapult our efforts in predicting conversion to psychosis. Overall, we saw that there were several joint models that showed improved prognostic accuracy over baseline models, indicating that short-term change may be much more informative than a simple baseline snapshot. And more specifically, we found that by adding longitudinal data from just a single SOPS item, significantly improved predictive performance, and future work could also further explore the significance of this particular negative symptom. Ultimately, this provides support for potentially having more frequent visits for high-risk individuals. And in the context of clinical trial design, these models could be used to help enrich the samples. Given the high levels of sensitivity and specificity that we achieved, this would help increase the confidence that we're adequately selecting for the desired sample to develop effective interventions. Okay, so that's all that I have for today. And I want to just quickly acknowledge, first of all, thank my advisor, Ty Cannon, in addition to the entire NABLES Consortium and my lab at Yale. And I would also finally like to thank the AMP Schizophrenia and ProNet leadership team for the opportunity to share my work at this meeting. Thank you so much.
Thank you very much, Michelle. I wanted to mention, since there's only a few seconds left in your minute, that you have a very interesting comment from Kristen Cadenhead that hopefully you will be able to respond to. And I want to again thank you everyone who's responding to the questions in the chat.